right. Next talk is about 2 years of BGP-EVPN to the host. And this is about a massive Kubernetes cluster called SCHIFF. I hope that you have an explanation for the name in your talk. And unfortunately, the original speaker couldn't make it. He's sick. But we have found our 2 replacements to give the talk. Please introduce yourself. The floor is yours.
Yeah. So, yeah, we are the volunteers who jumped in for Christopher, who is visible on the slide right now. Obviously, we are not him. He likes to do skiing, and he likes to do software and hardware. But yeah, this colleague is Maximilian Rink, who is working for Deutsche Telekom since a few years and started with a SCHIFF project. I've worked a bit longer for the company than he and joined the same project. And I would like to start with a short introduction into Kubernetes networking stuff and would hand over for that reason to Max.
Yeah, but you forgot your name, you're Jens Herzog.
Oh, yeah, I'm Jens Herzog as well, sorry.
So yeah, as we guess, not all of you are Kubernetes natives or have worked with Kubernetes before, so we prepared a quick primer how Kubernetes looks from a networking view. Because there are some primitives that you need to understand. First, what is a pod? So Kubernetes has a concept called pods. So individual containers are bunched together in a pod. That's the thing that an application runs in, basically. It's just Linux namespaces and C groups. You're separating them in the kernel using Linux namespaces. You assign limits on CPU usage, memory usage, all of that using C groups. Together, all of that construct in Kubernetes is called a pod. In the networking namespaces, you have all the necessary things for the networking to work, like netfitter rules. All of that is separated into separate Linux namespaces. You can have multiple of them on the same host. Kubernetes itself basically only creates empty network namespaces where the container runs. Everything else after that is pluggable. The networking part especially is called or implements the container networking interface. It's a pluggable configuration. Abbreviated with CNI or CNI plugins. There are a lot of different ones that you can choose to fulfill your needs. There are reference implementation, like just plain VF, MAC VLAN, IP VLAN bridge. There are bigger projects that some of you might have heard, like Calico or Cilium. We also use a special one called Coil. There are also meta implementations like Multus or Nokia's DAM. We will come to that specific one later. In general, CNIs implement a specific interface within Kubernetes. So ideally, they're completely pluggable. So if you want to replace a CNI, you should be able to in most circumstances. What does a CNI do? Like in our case, the simple form is basically you provide a VF peer from your pod to the host. And basically just connect everything together into layer 3 reachability. That's the simplest form that Kubernetes networking can take. You just have basic plain layer 3 reachability between pods. But how do you want to actually connect to those pods? So there's services. Services have endpoints. You need to discover them. So that's where core DNS comes in, usually. So you can just speak to a service instead of needing to find out the individual pods that are running in your cluster. You can just speak to one centralized service that can have a cluster IP that could be headless. So you just have it for service discovery. And there are other components in Kubernetes that are also just mostly pluggable, like kubeproxy, that do the actual translation from speaking to your service to the actual pods providing the service in the backend. In kubeproxy, that is basically just done by implementing some nut rules and throwing dices to actually do some load balancing. That's a rather simple implementation in that part. There are also load balancer IPs. They're also just mapped on services. Those come into play if you want to have external traffic in your cluster, which I guess most of you want to have. External service or load balancer IPs have an external traffic policy. They can either be local, so you only accept traffic on hosts that actually have a pod running that would accept that traffic, or cluster, where you would accept traffic on all nodes and just route it internally in the cluster. So for a normal one, local, you just have a DNAT incoming to the pod. Rather simple, you have the source IP address, and if you have nothing running on that node, you would just get traffic going into thin air, so you need to make sure that you're not routing traffic to nodes that don't have the service that you're trying to contact. With the policy type cluster, it's a bit easier. You can route traffic to every node, and it will always reach its destination, but you basically lose your source IP addresses because you do a DNAT and SNAT. On top of that, you might want to do more than just provide layer-free reachability. You might also want to do firewall policies, basically, so network policies, segment what applications are actually allowed to talk to other applications. You might want to segment communication to the outside. You might want to prevent things from the outside directly speaking to a certain sets of your pods and only allow certain CIDRs. That's where network policies come in. Those are CNI specific. In our case, we mostly use Calico to implement those, and Calico just basically generates IP tables rules. They get attached on the VF of the pod, so services itself, they don't have network policies. The pods that match those services do. In general, the networking requirements are not that complicated. We have pod-to-pod reachability, so pods inside the cluster need to be able to reach each other with load balancing. We need to have ingress and we need to have egress, because we need to reach things outside the cluster and we need to get reached from outside of the cluster. Most of those things can already be solved using BGP or BGP-EVPN. Yeah, that's basically what we are doing.
Yeah, we are now coming to the next part, which is das SCHIFF at Deutsche Telekom, and for which reason we did it and how we did this in our company. In a single word, we are trying to achieve an internal GitHub-based Kubernetes cluster as a service platform, which is almost exclusively built by using open source components, which is quite working well. And yeah, if we have a look on the complexity, our main customers are some mobile CNFs, in that case 5G Core, for example, or 5G Campus, the IMS and different more applications like that in general. And they need an interconnection between sometimes each other or to other important mobile applications in that case, which requires a lot of different VPN, VRF connections in maybe one or more than one backbone at once, which is highly complex and should not be a centralized configuration, because if you have a centralized configuration, the point of failure or the risk of a failure will be much higher than a decentralized configuration, as well in a multi-tenant fabric. And the goal was as well that the customer itself can configure its network, because it will not consume as much time than we do with that, and they bring a lot of people per application to do that stuff in general. And when we have a deeper look into our network complexity, you can see on the left side that there is the different VRFs, which could be, as I've mentioned, be in the same backbone or belong to different backbones. In the middle of the screen, you can see the multi-tenant network fabric, which is in our case just a normal spine leaf fabric. And on the right side, you can see different clusters, which will then use a different amount of VRFs depending on the customer needs. In addition, there are some telco requirements as well, because the most of the network functions we currently onboard on our platform are not cloud native. And for that reason, we have additional containerized network functions, CNF, which in the most cases use additional networks to connect to the needed services of the application. And in the most cases, in our case, is MAC VLAN, IP VLAN, and or SIOV for a specific customer. To handle that, there is a meta CNI needed. The meta CNI will take care of the orchestration, or it will orchestrate the other CNIs which are working for the specific workload, and it's possible to, or it's able to manage the multiple interfaces which will be used due to the customers. And the well-known CNIs for that will be Multus out of the Kubernetes Networking Plumbing Working Group and Nokia's DANM. Yeah, in our setup, you can see on the left side a figure about that. We have the node where the pod still is running on. You could see earlier from the normal Kubernetes networking stuff, which is running into a network namespace. A pod will ever run in our solution in a default VRF on the Linux kernel. And as we've mentioned, there is a possibility to bring different VRF to the customer depending on the customer needs. And this VRF will be brought to the cluster by using VXLAN, and in our solution every VRF has its own VNI. And yeah, to have the VXLAN topology working and all tunnels which are necessary are established, the underlay on the Linux server as well is used to advertise the loopback addresses as well from the server, and they will contain as well the loopback addresses of the different switches. Yeah, as you can see maybe already, we use VRFs quite a lot. It's usual that most customers, I guess, have around 3 or more VRFs at once. We have a problem with the route leaking on the Linux host itself. For that reason, we have some import filter because the pods need to have the route in the default table, and we are filtering that. In addition to that, we will also place, in case of MAC VLAN, for example, we will place a static Anycast gateway directly onto the server, which will prevent some packet loss issues we will see later on another slide. In addition to that, to configure all that manually would be a lot of work. The guy who was shown on the slides before, Christopher, invented the SCHIFF network operator, which is a tool which translates some custom resource definitions into netlink configuration, or in that case as well FRR configuration. And as mentioned, due to the Linux VRF underlay, we are using VXLAN in combination with BGP-EVPN and as well multi-protocol BGP. I guess it was one too much. No, there is one slide missing. No, it's here. Sorry. We have the caveats. In our case, we have not only cloud native network stuff, we have also SIOV enabled for some of our customers. SIOV is in general bypassing the Linux kernel, so you have no possibility to capture this packet on the host. And as well, for that reason, the kernel doesn't see the packet. There's also no encapsulation and decapsulation possible for VXLAN. And to solve that problem, we have currently the VTAP termination done on the fabric leaves. And then the traffic will be forwarded by just using VLAN to the generic or to the specific host where the workload is currently placed on. And in the future, we will have the VTAP on the NIC when we jump over to DPUs. The NIC can take over the VXLAN encapsulation, decapsulation. Beneath that, we have some caveats in the Linux kernel. The VRF route leaking for local endpoints is a pain because it's broken somewhere. We need to use, or without the L3 MDEV accept flag, it's quite not possible to do this VRF routing on our clusters. For the reason, the interfaces within the default VRF won't be reachable out of the specific VRFs. We will attach in addition to the cluster. And to have the exchange between the default table and the VRF, we will always have a virtual Ethernet pair between the VRF and the default VRF using BGP to exchange the incoming and the received and advertised routes for BGP in general. As well, every network namespace requires own net filter rule set, because every pod will bring its own network namespace. kubeproxy, and the CNI will write the rules already acting on all the traffic within the VRF. And for that reason, we have a quite big, or in general, the eBPF rule set to increase the performance and to bypass in the VRF the net filter rules, that this is only executed when the packet hits the default VRF. In addition to that, there would be an alternative solution where you can place a router in a separate network namespace and do everything there, but that's currently not our approach.
Yeah, we also hit quite a few FRR bugs in our last few years. For example, in production, we are running a known good, rather old FRR version. This is still out of the version 8.3 because every version since then had some critical bugs that that prevented us from rolling it out. Christopher added a list of all the current ones that we still have open here. There's also the big issue with the FRR configuration. So the network operator that we have basically templates FRR config on the host and then needs to reload FRR, which uses the FRR Python reload script, which mostly works, but occasionally also doesn't. So there also needs to be logic in there to recover from a reload failure. In general, FRR, if you want to use it, you should be aware that you need to spend time debugging it and probably upstreaming a lot of your findings, or at least filing issues for it. It's not a solution that you can just rely out of the box for that specific use case, and it will just magically work with no issues. In summary, yeah, we're running that for about 2 years, more than 2 years now. We have a humble beginning that we still need to somewhat design around, like as Jens mentioned. We want to take another look at Linux namespaces instead of VRFs. We had some issues with FRR on the hosts where we needed to spend quite a lot of time to debug things, especially when you had failures inside the fabric. That propagated to link flap or propagated to completely broken nodes that needed to an FRR restart to even work again. So the complete redundancy mechanisms weren't working in some FRR versions. Yeah. In general, we can with this design we can build a completely layer 2 free fabric, with the exception of SIOV. That's also one of the more interesting points for the future. So we are currently looking at DPUs, IPUs, smart NICs, depending on how you want to call it, to offload a lot of things onto those, both from a security separation standpoint. So our hosts are heavily tied into the fabric. There's no real separation between our hosts and the fabric. So if you break out of containers on the containers, you have direct fabric access, which is good and bad. Ideally, we would like to limit that. DPUs are one way to do that. The ecosystem, from the software perspective, isn't really mature, though. There isn't a solution that you can just buy that magically works. There isn't even a solution that Kubernetes somewhat integrates nicely. There are vendors that have their own proprietary ways or ideas of integrating DPUs inside Kubernetes and making that viable. We in general, don't like proprietary things. We try to build it open, and there currently isn't even an approach to have an upstream first integration into Kubernetes with DPUs, which is a bummer. Questions? We have quite a lot of time left, given that we basically played PowerPoint karaoke.
Yeah. Are there any questions? Anything from the chat? Come on, we have time. Where does the name come from, das SCHIFF?
Long story short, so we have our squad lead, Vuk. He started with a small project, actually introducing Kubernetes as a first feature inside DT. He called it Gaffelschoner. Kubernetes itself has a lot of ship-themed things around it, like Helm from Helmsman. A lot of the tools are named around shipping things. Like one of the more well-known container registries is just called Harbor. So the complete shipping theme just fitted, and we needed something internal to sell it, or some good naming to sell it.
Yeah, cool. Any more questions? Is there a question? No. Okay. All right. Thank you very much.